While talking about slope fields, we noted that the solution to a differential equation such as this is the y function, the function y, that would yield this particular derivative. Now, here is the slope field for this particular derivative. You'll notice that anywhere you are in the field, there is some sort of function that goes along in there. And that's why we said that there was a family of antiderivatives for any derivative. That there are an infinite number of possible solutions to any differential equation. Now, in initial value problems, they give us some information about the function that we're looking for. In this particular example, they gave us the point -1, 0, which is on our solution. So here, we're not looking for a general family of solutions. We're looking for one very specific solution, the one that goes to the point -1, 0, which I've highlighted right here. Well, what's the first step to going from dy over dx up to y? Well, the answer is we need to take the antiderivative of both sides. In other words, let's integrate both sides. So we'll take the integral of dy over dx, and we'll take the integral of the right-hand side as well. In reality, what we are really doing is we're moving this dx to the right-hand side. So we can multiply both sides by dx, and we get the integral of dy is equal to the integral of 9x squared minus 4x plus 5 dx. So really, we're multiplying both sides by dx, but for the sake of keeping things simple and not having too much work on our page, we'll just integrate both sides and just assume that there's a dx over here. When we solve differential equations later on, we are going to have to actually get the dx's on one side, the dy's on the other side, but here we have a dy dx all over here, and everything's in terms of x on the right-hand side. We can just kind of do this on the fly. But in reality, we are multiplying both sides by dx. Now, what is the antiderivative of dy? The answer is y plus c. However, we don't really need to put the plus c because we're going to move it to the right-hand side eventually. So we'll just put y here. And this is equal to the antiderivative of 9x squared, which is 3x cubed, minus, here we have 2x squared, plus 5x, and then of course here is our plus c. Now the c denotes that there are an infinite number of solutions that will yield this particular derivative, because the derivative of c is 0. They'll just go away when you take the derivative of that. However, we actually want to find what c is. We need c because we want to find a very particular solution here. But of course, they've given us some information. Namely, we have a point, -1, 0. Now, if you look at the slope field that we have, -1, 0 is right here. This c, however, doesn't really have anything to do with this point. In fact, c, in this particular example, is the y-intercept. Because if you were to plug 0 into x, you would get y is equal to c. We can note here that the y-intercept is 10. So I'm going to make a guess right now that c is probably going to be 10. But how can I figure this out? Well, I can plug in my point, -1, 0. So we have 0 is equal to -3 minus 2 minus 5 plus c. -3 minus 2 minus 5 is -10. Add 10 to both sides, and this yields that c is equal to 10, as we thought it would be. And so the particular solution to this differential equation with that initial value -1, 0 is y is equal to 3x cubed minus 2x squared plus 5x plus 10. This is the particular function y that we were looking for. Let's try another one. Here we have the derivative ds over dt is equal to cosine t plus sine t. And our initial condition is that when x is equal to pi, or when t is equal to pi, s is equal to 1. Well, let's multiply both sides by dt so we can get the t on the right-hand side. So here we have ds is equal to cosine t plus sine t dt. And of course now we can take the integral, or the antiderivative, of both sides. Now the antiderivative of ds is by definition s. And the integral of cosine t plus sine t. Well, the integral of cosine t is sine t. The integral of sine t is negative cosine t. And of course we have to include the plus c to indicate that there is a family of antiderivatives for ds dt. However, we're looking for the particular one that has the point pi comma 1. So let's plug 1 into s. Let's plug pi into t. So here we have 1 is equal to sine of pi is 0. Cosine of pi is negative 1. And here we have negative 1, which is positive 1, plus c. And this, of course, yields that c is equal to 0. So our particular solution to this initial value problem is that s is equal to sine t minus cosine t plus 0. And that right there is the answer.